membrane must be more negative, even though there's no negative charge. You don't have to have negative charge in order to have a negative membrane potential. Membrane potential, when it is measured inside versus out. So if I were to measure the membrane potential of this cell, if I took a little electrode made out of glass with some special fluid in it, with a little filament that went to some fancy equipment, and I either touched that membrane with a certain type of little electrode or poked it, I would be able to measure membrane potential. And what I would see is a negative membrane potential. Again, we measure it. Why would it be negative? Why not positive? Because it's not outside versus inside membrane, it's inside versus outside membrane when that particular value is measured. Are you with me? Okay, again, this is completely theoretical to help you understand how membrane potential is measured and what membrane potential is. We're comparing what's happening on the inner membrane to what's happening to the outer membrane. And if we were to add more positive charges to the inner membrane, this would be less negative. Those are things that we'll talk about later. If I were to add more positive charges to the outer membrane, this would be more negative. Things we'll talk about later. All right? So when it comes to membrane potential, it's inside membrane versus outside membrane. That's what the value is. And it rests, again, it's resting membrane potential. Resting membrane potential is negative. So let's put resting here, because that's what we're starting off with. We're not always going to be at rest. We'll be talking about other things. We're going to talk about an action potential, for example. Siebert calls it an electrical impulse. I'm going to give it a different name, and I'm going to show you how it works. And we're going to see that during that action potential, during that electrical impulse, membrane potential gets really positive. That's later. That's Wednesday. That's not tonight. We need to establish this first. All right? So far, so good? So again, resting membrane potential is a negative value. Why? Let's blow this up a little bit. There is net negative charge on the inner surface of the membrane as compared to the outer surface. Net, meaning if we had to compare the two in this particular instance. Just to make sure that we understand what we're saying here, let me just do this really quick. And you're going to tell me. We're just going to have negative charge now. So I'm going to take a couple of these away. These are negative charges, not dashes, but negative charges. If we were to measure the membrane potential of this cell, would it be positive or would it be negative the way that I have drawn it? Would it be negative or would it be positive? There's way more negative charge on the outside of the cell. There's not anywhere near as many negative charges on the inner membrane. Would the membrane potential be negative or would it be positive the way I draw this? It would be positive, right? Vm equals positive. Why? Well, let's think about this. The outer membrane is more negative, right? If the inner membrane is more negative, or the outer membrane is more negative, the inner membrane as compared to the outer membrane is what? More positive. Again, membrane potential, we compare what's happening on the inner membrane versus the outer membrane. So the inner membrane is more positive, even though there's no positive charges here. And so because the inner membrane is more positive than the outer membrane, our membrane potential is positive. So when we compare the two, right there, inner membrane versus outer membrane, this line is what counts to what that value is going to be. I said that at resting Vm, we have a negative membrane potential. Here, what's happening to the inner membrane versus the outer membrane, that's why membrane potential is positive, because of that line right there. I just introduced the first one because it's easier to see that the outer membrane is more negative. That's the reason I went in the order that I did. Are we good? Again, completely theoretical. There are no just negative charges across membranes. There are no just positive. This doesn't exist. What exists is that. That's what it looks like in real life. All right? So far, so good? Now I said we're going to concentrate on ions. Proteins are involved. We're not going to talk about the proteins that are involved in this. Well, we are going to talk about the ions. Which ones? Three main ones. And they're right here, sodium, potassium, and chloride. Now, earlier on this semester, we talked about the concentration of sodium and potassium, did we not? Concentration of sodium, is it high outside the cell or inside? You guys remember? Sodium's concentration is? Take a guess, given the way I've drawn this. It's higher outside, right? Potassium, complete opposite, right? Potassium concentration, high inside, low outside. Can you remind me what creates these gradients? Because that's what this is, right? This is a concentration gradient. What creates the sodium and the potassium gradient? Remind me. The sodium-potassium pump, correct? So the sodium-potassium pump, a primary active transporter, pumps sodium out of the cell, up its gradient, potassium into a cell, up its gradient. That's the reason that we have that distribution. And I had already introduced this to you at the beginning of the semester when we talked about transport. And at the time, I told you all you needed to know is sodium high outside, low inside. Potassium high inside, low outside. And I told you at the time that later on in the semester, you'd actually have to know the real numbers and real values. Well, now is that time. So if you look in your notes, outside sodium concentration, 145, you have to know that like the back of your hand. Inside sodium concentration, about 15. Potassium inside 135, outside 5. Chloride outside 110, inside 8. You have to know those. All right? Absolutely 100% have to know those. Now, when it comes to these concentration gradients, if we're talking about the movement of an ion passively, which way will sodium move? Into or out of the cell? Passively, not actively, but passively. Which way does it move? It'll move in, right? Sodium moves in, down its gradient, passively. This is active transport, correct? I'm talking about passive transport. Potassium, which way should it move, in or out of the cell? It should move out, down its gradient from a high concentration to a low concentration. Chloride, it's high outside, it's low inside. Which way is it going to move? Passively. In, down its gradient, again, passive. This is facilitated diffusion. We've talked about facilitated diffusion. We talked about it at the beginning of the semester, the transport. We're not allowed to forget anything here. All right? So we are going to have the movement of these ions, which is going to be key to what? Generating membrane potential. Why? Because it's the movement of the ions that counts. So we're going to get movement of these ions across the membrane because they have a reason to move. What's the reason? There's a concentration gradient. That's the reason for them to move, right? We learned this, right? The reason a molecule will move across the membrane passively is that there is a concentration gradient. High inside, low outside. High outside, low inside. That's what a gradient is. So that gives them a reason to move. What about the ability to move? What do we call that? If a cell has the ability to move across the membrane, what is that called? And it rhymes with ability. Permeability. So there are two things that are needed in order for an ion to move across the membrane, or any molecule, passively. A gradient and permeability. Permeability is also something that is measured, and I already told you that at the beginning of the semester when we talked about permeability in the transport chapter. That too is a measured value. Just like concentration is a measured value. Just like membrane potential is a measured value. Permeability is a measured value, and we can give it a number. You have to know those as well, like the back of your hand. At resting membrane potential, the permeability of sodium, the permeability of potassium, and the permeability of chloride are denoted here. The biggest number is for potassium. That value is 1. The smallest number is for sodium. That value is about 0.05. Chloride is 0.45. What do those values mean? The bigger the number, the more the movement. That's what that means. So if we had to draw that, so we just drew these concentration gradients in this picture. So this picture, we have the concentration gradients. We didn't give them the real numbers, we will in just a second, but that's what that picture is. If we had to draw the permeability picture, this is what we would draw. We would draw P, sodium, and we'll put a number there, and we'll draw an arrow that's very, very small for sodium to move across the membrane. Because at rest, permeability is little when it comes to sodium. For potassium, the permeability of potassium is huge compared to sodium. It's 1, it's 20 times bigger. So potassium, which moves out of the cell passively, give yourself a nice big arrow, because there's going to be way more potassium moving across the membrane. At rest, again, this is resting membrane potential we're talking about. Things are going to change, as we'll see on Wednesday. And then chloride is somewhere in between. The permeability of chloride is 0.45. It's going to move into the cell, and a pretty decent amount is at rest. So we get a visual here as to the movement of these ions, relative movement of these ions at rest. And again, this is measured, and permeability can go up or down. Permeability can be 0. Permeability of sodium can go much higher than 0.05. Okay, permeability of potassium can go much lower than 1. The bigger the number, the more the movement. So, as we increase permeability, P, you increase movement across the membrane. And then obviously the opposite is going to hold true. When you decrease permeability, again, it's measured. When you decrease permeability, you decrease the movement of the ion, we're talking specifically about ions, across the membrane. Okay? So a bunch of facts to start with. Now that we have all these facts, now that we've established many of the things that we need to understand membrane potential, let's see how it's done. And again, you have to know these values like the back of your hand, but we're going to draw. All right? So, what we have here at rest, we have these concentrations, we have these permeabilities. The concentration gradient and the permeabilities create an environment that dictates the movement of these ions across the membrane. The concentration gradient will dictate which way they move. The permeabilities will dictate how much moves across the membrane. So we're going to put those two things together along with these values, and what we're going to draw is this picture from scratch. And that picture from scratch is all those words right there. Those words right there tell you how resting membrane potential is generated. Those words right there. And when we're done with this picture, we're going to have a picture that looks similar to this one, but not exactly that. All right? So what we're going to do now, how is membrane potential generated? That's what we're going to do. Okay? Finally, that's what we get to. So we're going to draw a cell. So here's our cell. All right? We're going to have our sodium and our potassium and our chloride concentrations, but we're going to draw the real numbers. So sodium concentration outside of the cell is about 145 milliequivalents per liter. That's the osmolality of sodium on the outside of this cell. Okay, we know what osmolality is, right? It's a measure of the concentration of ions. We're measuring specifically the osmolality of sodium, and it happens to be about 145. If we measure the osmolality of sodium inside the cell, it would be about 15 milliequivalents per liter. All right? Which is actually osmolarity, but we don't have to get that technical about things, because they're both the same thing inside the body. Potassium, 135 inside the cell, and it's about 5. I put equal, let's put about, because it's going to vary a little bit. We know that everything in the body has a normal range. And then chloride, let's stick chloride way over here. It's about 110 out here, and inside the cell, it's about 8. Again, you have to know these values like the back of your hand. You have to memorize these values so that you can understand membrane potential. Okay? Now, these are ions. They're positively and they're negatively charged. Can they move across the membrane by themselves through simple diffusion? Yes or no? Nope. What can move across the membrane via simple diffusion? Small what? Soluble, fat-soluble molecules and gases can move across the membrane through simple diffusion. Well, these cannot do that. They need help. They need to be facilitated. So this is going to be facilitated diffusion through channels. And these channels that these ions are moving through to generate a resting membrane potential have a special name. They're called leak channels. And so we're